Orogeny refers to forces and events leading to a large structural deformation of the Earth's lithosphere due to the interaction between tectonic plates. Orogens or orogenic belts develop when a continental plate is crumpled and is pushed upwards to form mountain ranges, and involve a great range of geological processes collectively called orogenesis. The word orogeny comes from the Greek, and it is the primary mechanism by which mountains are built on continents. Geomorphology is the study of landforms and the processes that shape them. Physiography. Formation of an orogen is accomplished in part by the tectonic processes of subduction, where a continent rides forcefully over an oceanic plate, or convergence of two or more continents. Orogeny usually produces long arcuate structures, known as orogenic belts. Generally, orogenic belts consist of long parallel strips of rock exhibiting similar characteristics along the length of the belt. Orogenic belts are associated with subduction zones, which consume crust, produce volcanoes, and build island arcs. The arcuate structure is attributed to the rigidity of the descending plate, and island arc cusps are related to tears in the descending lithosphere. These island arcs may be added to a continent during an orogenic event. The processes of orogeny can take tens of millions of years and build mountains from plains or the ocean floor. The topographic height of orogenic mountains is related to the principle of isostasy, that is, a balance of the downward gravitational force upon an upthrust mountain range and the buoyant upward forces exerted by the dense underlying mantle. Frequently, rock formations that undergo orogeny are severely deformed and undergo metamorphism. During orogeny, deeply buried rocks may be pushed to the surface. Sea bottom and nearshore material may cover some or all of the orogenic area. If the orogeny is due to two continents colliding, the resulting mountains can be very high. An orogenic event may be studied as a tectonic structural event, as a geographical event, and a chronological event. Orogenic events cause distinctive structural phenomena related to tectonic activity, affect rocks and crust in particular regions, and happen within a specific period. Orogen. An orogeny produces an orogen, or range fall-and basin system. The fall-and basin forms ahead of the orogen due mainly to loading and resulting flexure of the lithosphere by the developing mountain belt. A typical fall-and basin is subdivided into a wedge-top basin above the active orogenic wedge, the foredeep immediately beyond the active front, a forebulge higher flexural origin and a back bulge area beyond, although not all of these are present in all fall-and basin systems. The basin migrates with the orogenic front and early deposited fall-and basin sediments become progressively involved in folding and thrusting. Sediments deposited in the fall-and basin are mainly derived from the erosion of the actively uplifting rocks of the mountain range, although some sediments are derived from the foreland. The fill of many such basins shows a change in time from deep-water marine through shallow water to continental sediments. Orogenic cycle. Although orogeny involves plate tectonics, the tectonic forces result in a variety of associated phenomena, including magmatism, metamorphism, crustal melting, and crustal thickening. Just what happens in a specific orogen depends upon the strength and rheology of the continental lithosphere, and how these properties change during orogenesis. In addition to orogeny, the orogen once formed is subject to other processes, such as sedimentation and erosion. The sequence of repeated cycles of sedimentation, deposition and erosion, followed by burial and metamorphism, and then by formation of granitic batholiths and tectonic uplift to form mountain chains, is called the orogenic cycle. For example, the Caledonian orogeny refers to the Silurian and Devonian events that resulted from the collision of Laurentia with eastern Abylonia and other former fragments of Gondwana. The Caledonian orogen resulted from these events and various others that are part of its peculiar orogenic cycle. In summary, an orogeny is a long-lived deformational episode during which many geological phenomena play a role. The orogeny of an orogen is only part of the orogen's orogenic cycle. Erosion. Erosion is a subsequent phase of the orogenic cycle. Erosion inevitably removes much of the mountains, exposing the core or mountain roots. Such exhumation may be helped by isostatic movements balancing out the buoyancy of the evolving orogen. Debate exists about the extent to which erosion modifies the patterns of tectonic deformation. Thus, the final form of the majority of old orogenic belts is a long arcuate strip of crystalline metamorphic rocks sequentially below younger sediments which are thrust atop them and dip away from the orogenic core. An orogen may be almost completely eroded away, and only recognizable by studying rocks that bear traces of orogenesis. Orogens are usually long, thin, arcuate tracts of rock that have a pronounced linear structure resulting in terranes or blocks of deformed rocks, separated generally by suture zones or dipping thrust faults. These thrust faults carry relatively thin slices of rock from the core of the shortening orogen out toward the margins, and are intimately associated with folds and the development of metamorphism. Biology the study of orogeny, coupled with biogeography, geography and mid-ocean ridges in the 1950s and 1960s, contributed greatly to the theory of plate tectonics. Even at a very early stage, life played a significant role in the continued existence of oceans, by affecting the composition of the atmosphere. The existence of oceans is critical to sea floor spreading and subduction. Relationship to mountain building Mountain formation occurs through a number of mechanisms. Mountain complexes result from irregular successions of tectonic responses due to sea floor spreading, shifting lithosphere plates, transform faults, and colliding, coupled and uncoupled continental margins. Large modern orogenies often lie on the margins of continents. The Alleghenian, Laramide, and Andean orogenies are examples of these in the Americas. Older inactive orogenies, such as the Algerman, Pinocchine and Antler, are represented by deformed rocks and sedimentary basins further inland. Areas that are rifting apart, such as mid-ocean ridges and the East African Rift, have mountains due to thermal buoyancy related to the hot mantle underneath them. This thermal buoyancy is known as dynamic topography. In strike-slip orogens, such as the San Andreas Fault, restraining bends result in regions of localized crustal shortening and mountain building without a plate margin-wide orogeny. Hotspot volcanism results in the formation of isolated mountains and mountain chains that are not necessarily on tectonic plate boundaries. Regions can also experience uplift as a result of delamination of the lithosphere, in which an unstable portion of cold lithospheric root drips down into the mantle, decreasing the density of the lithosphere and causing buoyant uplift. An example is the Sierra Nevada in California. This range of fault block mountains experienced renewed uplift after a delamination of the lithosphere beneath them. Finally, uplift and erosion related to orogenesis can create local topographic highs. Mount Rundle on the Trans-Canada Highway between Banff and Canmore provides a classic example of a mountain cut in dipping layered rocks. Millions of years ago a collision caused an orogeny forcing horizontal layers of an ancient ocean crust to be thrust up at an angle of 50°-60 degree. That left Rundle with one sweeping, tree-lined smooth face, and one sharp, steep face where the edge of the uplifted layers are exposed. The collision causing the Columbia orogeny occurred about 175 million years ago, and as the shock wave moved eastward, it forced huge masses of rock to crack and slide up over its neighbors. This is known as thrust faulting and was instrumental in the formation of the Rockies. The shock wave began piling up the western ranges, and then the main ranges, around 120 million years ago. History of the concept. Before the development of geologic concepts during the 19th century, the presence of marine fossils in mountains was explained in Christian contexts as a result of the biblical deluge. This was an extension of Neoplatonic thought, which influenced early Christian writers. The 13th-century Dominican scholar Albert the Great posited that, as erosion was known to occur, there must be some process whereby new mountains and other landforms were thrust up, or else there would eventually be no land. He suggested that marine fossils in mountainsides must once have been at the sea floor. Orogeny was used by Ammons Gressley and Jules Thorman as orogenic in terms of the creation of mountain elevations, as the term mountain building was still used to describe the processes. Elie de Beaumont used the evocative jaws of a vice theory to explain orogeny, but was more concerned with the height rather than the implicit structures created by and contained in orogenic belts. His theory essentially held that mountains were created by the squeezing of certain rocks. Edouard Suess recognized the importance of horizontal movement of rocks. The concept of a precursor Josy-incline or initial downward warping of the solid Earth prompted James Dwight Downer to include the concept of compression in the theories surrounding mountain building. With hindsight, we can discount Downer's conjecture that this contraction was due to the cooling of the Earth. The cooling Earth theory was the chief paradigm for most geologists until the 1960s. It was, in the context of orogeny, fiercely contested by proponents of vertical movements in the crust, or convection within the asthenosphere or mantle. Gustav Steinmann recognized different classes of orogenic belts, including the alpine-type orogenic belt, typified by a fly and mollusk geometry to the sediments. Ophiolite sequences, thalliatic basalts, and a nappe-style fold structure. In terms of recognizing orogeny as an event, Leopold von Buch recognized that orogenes could be placed in time by bracketing between the youngest deformed rock and the oldest undeformed rock, a principle which is still in use today, though commonly investigated by geochronology using radiometric dating. H. J. Zwart drew attention to the metamorphic differences in orogenic belts, proposing three types, modified by W. S. Pitcher in 1979 and further modified as Hercynotype. Shallow, low-pressure metamorphism. Thin metamorphic zones, metamorphism dependent on increase in temperature, abundant granite and migmatite, few ophiolites, ultramafic rocks virtually absent, very wide erosion with small and slow uplift, nappe structures rare. Alpinotype. Deep, high-pressure, thick metamorphic zones, metamorphism of many phases, dependent on decrease in pressure, few granites or migmatites, abundant ophiolites with ultramafic rocks, relatively narrow erosion with large and rapid uplift, nappe structures predominant. Cordilleran type. Dominated by calc-alkaline igneous rocks, andesites, granite batholiths, general lack of migmatites, low geothermal gradient, lack of ophiolite and abyssal sedimentary rocks, low-pressure metamorphism, moderate uplift, lack of nappes. The advent of plate tectonics has explained the vast majority of orogenic belts and their features. The cooling Earth theory is dispensed with, and tifrotectonic-style vertical movements have been explained primarily by the process of isostasy. Some oddities exist, where simple collisional tectonics are modified in a transform plate boundary, such as in New Zealand, or where island arc orogenies, for instance in New Guinea, occur away from a continental backstop. Further complications such as Proterozoic continent-continent collisional orogens, explicitly the Musgrave Block in Australia, previously inexplicable, are being brought to light with the advent of seismic imaging techniques which can resolve the deep crust structure of orogenic belts. See also. Notes. References: A Permel de Beaumont, J.B., 1852. Notice sur les systèmes de montagnes, Bertrand, Paris, 1543 pp. Buch, L. von, 1902. Gesammelschriften, Rath and Eck, Berlin. Downer, James D. On some results of the Earth's contraction from cooling, including a discussion of the origins of mountains, and the nature of the Earth's interior. American Journal of Science 5, 423–443. Dennis, John G., 1982. Orogeny, Benchmark Papers in Geology, Volumes 62, Hutchinson Ross Publishing Company, New York, ISBN 0-87933-394-4, Hall, J., 1859. Paleontology of New York, in New York National Survey No. 3, Part 1, 533 p. Suess, Edouard, 1875. Dienstung der Alpen lit. The Origin of the Alps, Braumer 1/4 Layer, Vienna, 168 p. Harms, Brady, Cheney, 2006. Exploring the Proterozoic Big Sky Orogeny in Southwest Montana, 19th Annual Keck Symposium. Kevin Jones. Mountain Building in Scotland, Science, a Level 3 Core Series. Open University Worldwide Limited. ISBN 0-7492-5 5847-0. Provides a detailed history of a number of orogens, including the Caledonian orogeny, which lasted from the late Cambrian to the Devonian, with the main collisional events occurring during Ordovician and Silurian times. Tom McCann, ed. Precambrian and Paleozoic. The Geology of Central Europe 1. Geological Society of London. ISBN 1-86239-245-5. Is one of a two-volume exposition of the geology of Central Europe with a discussion of major orogens. Suzanne Marburg K. Barker A. Ramos. William A. Dickinson, eds. Backbone of the Americas, Shallow Subduction, Plateau Uplift, and Ridge and Terrain Collision. Memoir 204. Geological Society of America. ISBN 0-8137-1204-1. Evolution of the Cordilleras of the Americas from a Multidisciplinary Perspective from a Symposium held in Mendoza, Argentina. External links, Maps of the Akkadian and Tectonic Orogenies, Antarctic Geology.